Have you ever stopped to think about how a Formula One car is actually created? We're not just talking about assembling a powerful engine or fitting four state-of-the-art tires. We're talking about a true masterpiece of modern engineering, involving thousands of hours of simulations, design, construction with cutting-edge materials, and exhaustive testing. And the most impressive thing? All of this happens at such an extreme level of precision that a single non-standard part can cost not just a race, but an entire championship. In today's video, we'll open the doors to the most secret backstage of Formula One and reveal how the 2025 season cars are made, the most advanced in history. And let's go back in time and show you too how the brave machines of the 1950s were built, when driver and car were almost one. So, if you're a fan of motorsports, technology, or simply want to understand why a Formula One car is worth tens of millions of dollars, stay with me until the end of this video, subscribe, and like the channel. When Formula One officially began in 1950, no one could have imagined the technological monster it would become 75 years later. Back then, racing cars were closer to modified everyday vehicles than to machines designed with artificial intelligence in multi-million-dollar laboratories. What you're about to hear is a journey back in time to the golden years of engineering in the race, a time when cars were built almost by sheer guts and guts, with rudimentary structures, little safety, and an obsession with speed. This is the starting point of Formula One, an era where drivers' skills were put to the test in indomitable machines, created almost by hand. To understand how cars were built, we first need to talk about the Alfa Romeo 158, the star of the first Formula One World Championship in 1950. This car was originally developed in the 1930s, before World War II, and was later adapted to the new F1 regulations. Its chassis was tubular, made of hand-welded steel, forming the famous base frame. This type of structure resembled a cage, with each metal tube positioned to absorb as little impact as possible, not for safety reasons, but for rigidity reasons. No carbon monocoques, as we see today. Those cars were practically metal skeletons with wheels and an engine. According to Alfa Romeo's technical archives and FIA records, the average weight of cars at that time was around 700 to 800 kilograms, and dynamic balance was determined almost by feel, without any precise aerodynamic analysis. New materials used reflected the industrial reality of the time. Most cars were built with hand-beaten aluminum panels placed over a tubular steel frame. Aluminum was light and relatively strong, but extremely vulnerable to dents and structural failures. Furthermore, the engine was almost always installed in the front part of the car, which compromised weight distribution. In many cases, the engines were large, water-cooled 8 or even 12-cylinder engines that produced between 150 and 300 horsepower. This seems small compared to the more than 1,000 horsepower of today's hybrid engines, but it was enough to push these machines to over 175 miles per hour, 280 kilometers per hour, without wings, without traction control, and with very thin, low-grip tires. Not to mention the brakes to drum, that is, an extremely limited technology that suffered from overheating, especially on more demanding circuits such as Spa-Francorchamps or Nürburgring. The construction of these cars was almost artisanal. There was no clear division between engineers, mechanics, and designers as there is today. In many teams, the same group of men who designed the parts were also responsible for welding them, assembling the engines, and testing the cars on the track. Testing was often done by hand, with a driver turning laps and giving feedback directly to the mechanic. Suspension adjustments were made with a wrench and hammer, and the cars, in general, were not standardized. This meant that each team adapted the car as best they could, including with improvised parts. An interesting fact, some small teams, such as Connaught or Cooper Car Company, used parts from street vehicles, such as adapted transmissions, axles, and fuel tanks. And speaking of security, or rather, lack of it, it is worth remembering that the cars of that time, they didn't have seat belts. That's right. The logic was that, in the event of an accident, the driver would be thrown out of the car and would have a better chance of survival than being trapped in a structure that would catch fire. The cockpits were extremely cramped, lined with leather or canvas, and protected only by a minimal aluminum frame. The helmets? Open face, like those worn by World War II aviation pilots. There was no Hans device, no survival cell, not even an impact-absorbing structure. As pilots of the time said, either you finished the race or the race finished with you. Another point is that aerodynamics, it was not an applied science yet. Cars of the 1950s had shapes inspired by airplane fuselages, but not with a focus on downforce. The goal was simply to reduce drag, air resistance. Wings wouldn't appear on cars until the 1960s. Until then, straight-line speeds were high, but in corners, the car was literally pushed by the driver's body and skill. Stirling Moss, Juan Manuel Fangio, and Alberto Ascari were geniuses for being able to tame these beasts with almost no help from the machine. For all these reasons, when we look at a current Formula One car, full of sensors, carbon fiber, and digital simulation, it's almost unbelievable to imagine that it all started like this, with men, steel pipes, courage, and a lot of improvisation. They lacked the support of modern science, nor sufficient protection. But it was this foundation that shaped Formula One to its core: speed, risk, and constant innovation. Before I continue, please like and subscribe to the channel so that the YouTube algorithm recommends this video. And let's go. If the 1950s marked the birth of Formula One as a quasi-artisanal challenge, it was from the 1970s to the 2000s that the sport began to transform into a true laboratory of extreme innovation. The evolution was so aggressive that, in less than 3 decades, Formula One left behind manual construction and improvised cars, moving to operate with aerospace engineering tools, high-tech composite materials, and solutions that would shape not only the future of motorsports, but the automotive industry itself. And all of this began to consolidate with a name that today is synonymous with technical revolution: carbon fiber. But before that, it's impossible to discuss F1's technological evolution without addressing the turbocharged era, which dominated the scene between the late 1970s and mid-1980s. In 1977, Renault dared to introduce turbocharged engines to Formula One with the RS01. The proposal seemed risky: use a small 1.5L engine with fewer cylinders to compete with the dominant naturally aspirated V8S and V12S. However, the turbo engine offered a massive advantage: significantly more power in a compact size. In the following years, BMW, Ferrari, Honda, and other brands jumped on the bandwagon, and soon their engines were delivering over 1,200 horsepower during qualifying sessions. That's right, 1,200 horsepower in a car weighing less than 600 kilograms, with tires and brakes still underdeveloped to control it all. The result? Thrilling races, yes, but also a dramatic increase in accidents and mechanical failures. It was precisely in this extreme scenario that engineers realized they needed to reinvent more than just the engines. It was time to change the car's structures. And here comes the major milestone of 1981, when McLaren, led by engineer John Barnard, launched the MP4-1, the first Formula One car in history with a carbon fiber chassis. Until then, even the most advanced cars used metal alloys such as aluminum or improved tubular structures. Carbon fiber, used for the first time in its entirety, offered a seemingly magical combination: lightness, rigidity, and impact resistance far superior to traditional aluminum. The design, initially viewed with suspicion, soon proved its worth after a brutal crash by John Watson at Monza. The car was destroyed, but the cockpit remained intact. From that moment on, the carbon fiber monocoque became the absolute standard in Formula One, and remains so to this day. Beyond the structural revolution, the 1980s and 1990s also marked the beginning of the modern aerodynamic era. While the addition of wings was experimental in the 1960s, in the following years it became a science. Teams like Lotus, Williams, and Ferrari began using wind tunnels, spaces where scale models of cars were tested in air currents to study aerodynamic behavior. The goal was clear: generate the greatest possible downforce without compromising straight-line speed. Over time, this evolved into the use of CFD, computational fluid dynamics, digital simulations of airflow around the car, which are now standard, but began tentatively in the 1990s. Another important milestone was the arrival of onboard electronics. In the late 1980s and early 1990s, systems such as traction control, semi-automatic transmissions, introduced by Ferrari with the 640 in 1989, real-time telemetry, and active suspension began to be tested. The pinnacle came with the Williams FW14B in 1992, a car so ahead of its time that it practically drove itself with the help of sensors and algorithms. Nigel Mansell's performance in that car was so dominant that the FIA had to take action. Several technologies were temporarily banned for detracting from the driver's merit. But the seed of automation had been planted. During this same period, safety began to be treated as a science rather than a secondary concern. After tragedies like those involving Gilles Villeneuve, 1982, and Elio De Angelis, 1986, the FIA began requiring crash tests for chassis, larger runoff areas on circuits, and stricter rules on survival cell design. But it was only after the fateful 1994 Imola Grand Prix, which killed Ayrton Senna and Roland Ratzenberger, that safety became a top priority. Cockpits were reinforced, the sides were fitted with impact absorbers, and protective measures extended to helmets, horns, and six-point harnesses. Finally, we must mention how factories became true technological centers of cutting-edge engineering. Teams like Ferrari and McLaren stopped operating in workshops and started operating in full-fledged headquarters, with separate aerodynamics, simulation, composite materials, and engine departments. It was during this era that the first driving simulators emerged, allowing drivers to virtually drive the car before the physical part even existed. This is standard practice today, but it emerged during this transition period. Today, in 2025, Formula One cars are not just vehicles. They are true works of futuristic engineering, created with millimeter-level precision that borders on the absurd. It all starts with digital design and the intensive use of CFD, computational fluid dynamics, simulations. Before even a single part is physically molded, engineers create hundreds of versions of the car using high-performance software, such as Siemens NX or CUDIA V6. This software simulates the behavior of air over every surface of the car, testing thousands of variations of front wings, side wings, diffusers, and rear wings in a matter of hours. Thanks to this data, the team already knows exactly how the car should behave before a physical prototype even exists. Furthermore, these virtual models are connected to machine learning systems, which cross-reference real-time data with the history of previous seasons, helping to predict structural or aerodynamic failures weeks in advance. With the data digitally validated, it's time to produce the monocoque, the car's central structure. This part is molded entirely from carbon fiber, the lightest and strongest material in the industry. Unlike metals, carbon fiber is made from extremely thin layers of composite fabric applied manually by specialized technicians, layer by layer, within a negative mold. This structure then goes into an autoclave, a pressurized chamber that heats the part to over 130 degrees Celsius and presses the carbon with over 6 atmospheres, curing the material until it reaches the desired rigidity. This process can take up to 24 hours, and each monocoque undergoes mandatory FIA impact tests, where sensors verify that it meets all safety criteria. It's worth remembering that the monocoque also functions as a survival cell. Hence, it's designed to absorb impacts of up to 60 G without compromising the driver's safety. Alongside chassis manufacturing, other car parts are produced simultaneously, using a highly efficient logistics system. Wings, cooling ducts, suspension arms, and aerodynamic covers are almost always printed on industrial 3D printers or milled on 5-axis CNC machines. This ensures not only design accuracy, but also production speed. Some teams, like Red Bull Racing, produce more than 2,000 aerodynamic upgrades per season, changing parts at each race based on new data. All of this is possible thanks to internal departments that operate like true independent factories, with casting, welding, quality control, and laser scanning inspection. The powertrain, the heart of the car, is a spectacle in itself. In 2025, the engines will follow the 1.6L V6 turbo hybrid configuration with MGUK and MGUH, but with significant upgrades in efficiency and integration. Each engine is assembled by a separate team, such as Mercedes-AMG HPP, high-performance powertrains, and undergoes dozens of tests on dynamic benches before being mated to the chassis. The complexity here is enormous. There are more than 1,000 sensors spread throughout the car, monitoring temperature, pressure, vibration, and performance in real time. This data is transmitted via telemetry to the team during practice and races, allowing for instant strategic adjustments. The car's final assembly takes place in a clean room, similar to those used in the aerospace industry. Technicians wearing anti-static suits assemble the car piece by piece, using digital torque wrenches that ensure each bolt is tightened with pinpoint precision. Nothing is done by eye. Even the placement of sponsor stickers is measured to avoid interfering with aerodynamics. And before any part hits the track, it undergoes rigorous testing, including high-frequency vibration, thermal stress, and even laser testing to detect microcracks invisible to the naked eye. Additionally, drivers undergo dozens of sessions in ultra-realistic simulators, where every aspect of the car can be virtually tested. These simulators, like those used by Ferrari and McLaren, reproduce not only the car's physical behavior with hundredths of a second precision, but also include weather variations, tire wear, and even light reflections. It's in these simulators that drivers practice new setups, try out updates before they hit the track, and help guide the car's technical development. Everything you've heard so far shows how Formula One in 2025 is a fusion of precision engineering, artificial intelligence, and human performance at the highest possible level. No other motorsport category, and few industries in the world, operate with this level of technical demand. But tell me, what did you think of this video? Leave a comment below. I'd love to hear your opinion. Like and subscribe to the channel so you don't miss a thing.